In this video, I'm going to go through the A-level chemistry paper, OCR 2020 paper. This is paper 2, so it's mostly organic chemistry. I'll do just the first half in this video and the second half in a later one. Okay. Right. Okay, so the multiple choice section. The first one, what's the name of this compound? So I would probably start by numbering the carbon atoms. 1, 2, 3, 4, 5. You need to start from that end. So the alkene has the lowest number because that's the functional group. Okay, so it is going to be pentene, pentuene, and it's got a bromine on number 3 there, so it's 3-bromo pentuene. And now when you see is the E or the Z isomer, well, let's have a look at the blue carbon there. Okay, so the highest priority group on the blue carbon is going to be the bromine because that's got the biggest molecular weight. And on the green carbon, the highest priority is the methyl group. So they're opposite each other, so it's E. So the answer is E, 3-bromopentuene. Okay, there's about the carbon-carbon bond. But the carbon-carbon bond is more polar. Neither of them are polar, so it's not that one. A sigma bond is stronger than the pi bond. That is true. It's slightly stronger. Let's check the others. This bond angle in ethane, well, that's 109.5, whereas in ethene it's 120, so that's not true. And the sigma bond is formed by the sideways overlap of p orbitals. Well, that's not the sigma bond, that's the pi bond. So B is the right answer there. Which of these reagents will not react with this compound? Now, this compound has got an alcohol group and a carboxylic acid group. Sodium cyanide in ethanol. The cyanide ion is a nucleophile, but it's not going to react with anything there. Okay, so that is going to be the one that doesn't react. Let's check the others. Ethanol in the presence of an acid catalyst, well, that's going to esterify with the carboxylic acid group, so that will react. That's an acid anhydride that will react with the alcohol group to form an ester. Concentrated sulfuric acid, well, that will dehydrate an alcohol to an alkene, so that will react. So A is the answer there. Okay, which compound can be refluxed with acidified potassium dichromate to form an organic product with the formula C5H8O2? Now we can see from the ratio of carbons to hydrogens there, that has got to contain 2 double bonds. Okay, and obviously we've got to have 2 oxygens in there. They've all got the right number of hydrogen carbons, so forget about that. Right, so when can you oxidize A? You can't oxidize A because it's a tertiary alcohol. That there is that's attached to 3 of the carbons, so you can't oxidize that. So that is not going to give us you're not going to oxidize it to a ketone to get another double. We need another double bond. It's not going to be that one. B, can you oxidize B? You can oxidize B. It's a secondary alcohol that's going to oxidize it to a ketone, so that looks good. That's right. That one will give you C5H8O2, and we need to just check the other ones now. C, can you oxidize? Oh, actually, that's wrong. I'll tell you why that's wrong. That's not the answer. Right, you can oxidize that to a ketone, but look, this is an aldehyde. You're going to oxidize that to a carboxylic acid. So you'd end up with 3 oxygens in the formula there. Okay, so it's not that one. And the answer is C, because that's a secondary alcohol. You can oxidize it to a ketone and give it another double bond, which we need. That's the one. And D, why can't you do D? Well, D, you will oxidize that primary alcohol to a carboxylic acid, and you'll end up with 3 oxygens. You'll actually end up with 4 oxygens, because then you'll also oxidize that aldehyde to a carboxylic acid as well. So the answer is C. Which shows a section of polypropene. Well, propene is like this. So how's that going to polymerize? Right, you're going to lose the double bond there, and you're going to form that. Okay, so you can see there that that D is the answer there. These two are wrong because they've got double bonds in them, and that is polyethene, isn't it? That one, so you couldn't get that. You've got to have this branch with the methyl. So D is the correct answer. Which alcohol reacts with an acid to form a mixture of stereoisomers? Okay, this is quite a tricky question, right? So when you're reacting with an alcohol, you are going to dehydrate them to an alkene. And of course, this kind of stereoisomerism we're talking about is geometric isomerism. So that's the first one, 3-methyl butane 2-ol, right? If you dehydrate that, you're going to lose that OH. Sorry. And you're going to lose that OH, and you're going to get a double bond there. Okay, now that can't show EZ isomerism because that you've got a methyl group there, and you've got two things of the same on the carbon there, so that can't work. Okay. Let's say if we dehydrated it the other way, so if we're going to lose, if we form the double bond there, that's not going to work either because you're going to have 2 hydrogens on this carbon. So you can't have EZ isomers there. Pentan 1-ol, let's just quickly draw that. Okay, so you've got, right. So in pentan 1-ol, you are going to remove this and you're going to form the double bond there. Well, you can see again, this N carbon has got 2 hydrogens on it, so it can't show EZ isomerism. Let's try C, 2-methyl hexane 2-ol. All right. Okay, so we've got a methyl group on there and an OH on there. Okay, so if we lose that OH and form the double bond there, you can see that can't show EZ isomerism because you've got 2 methyl groups there on the same carbon, 2 the same. Of course, we could, right, if you could form the double bond there, then that can't either because you're going to have 2 hydrogens on that carbon. So that can't do it. So it's got to be D, heptane 4-ol. Let's just check that. Okay, so okay, for 1, 2, 3, 4. Okay, we've got the OH there. Going to dehydrate that. Okay, so we're going to lose that. And you can see that that will show EZ isomerism because well, you've got a hydrogen there and you've got this ethyl group. You've got 2 different groups on that carbon. And on this carbon, well, you've got, again, we've got that group there and we've got a hydrogen. So 2 different groups on both carbons. So the answer is D. Okay, number 7. Which of the following reacts with ethanoic acid and phenol? Okay, so ethanoic acid is an acid. You are going to, and phenol is a much weaker acid, but it is still much weaker. But you can lose the H of phenol there, and you can lose that H there. So let's see if this, well, first of all, neither of them are going to, well, phenol will react with bromine. There's no double bond in the carboxylic acid, ethanoic acid. So that's not going to react. Calcium carbonate will react with, let's see, calcium carbonate is not a very strong base, okay? So it will react with the ethanoic acid because that's a strongish weak acid, but it won't react. It's not strong enough base to react with the phenol. The phenol is too weak an acid, so that's not going to react with the phenol. Methanol and an acid catalyst, well, that will react with phenol to form an ester because, yeah, you've got an OH there, but oh, sorry, wrong way around. It won't react with phenol because there's no carboxylic acid, but it will react with the carboxylic acid to form an ester. So that means it's got to be A, and it is A because, right, potassium hydroxide is a strong base. And so it's strong enough to react even with phenol, which is a very weak acid. And of course, it will react with ethanoic acid because that's a reasonably strong weak acid. So the answer is A. Okay, which of these produces the smallest number of peaks in the NMR spectrum? Okay, so that's going to, let's see. So you're going to get 1 peak there, 1, they're equivalent, 2, 3, 4. You're going to get 5 peaks with that one. Let's see, B, you're going to get those two are the same, 1, 2, 3, 4, and that's also going to give you 5 as well. C, right, so you're going to give, that's going to be, they're all the same, 1, that's unique, 2, 3, 4, that's going to give you 4 peaks. And let's try D. D is going to give us 1, 2, 3, these are the same, 4 and 5. So the answer there is C, because that only gives us 4 peaks and the others are all 5. Okay. Okay, number 9. What's the structural formula of ethyl 3-methyl butanoate? Right, so let's draw 3-methyl butanoic acid first. So we're going to have, there is 3-methyl butanoic acid, right? It's an ester, it's the ethyl ester of that. So we're going to have that there, like that. Okay, so how would we draw that in shorthand? Well, we can see we've got CH3 twice there, and then got CH. Where's the one with CH? This one here, isn't it? You see CH3 twice, and then we've got CH for that one. Then we've got CH2 for that one. And then we've got the ester functional group and the, yeah, so D is the answer there. Okay. Okay, what is the number of alicyclic structural isomers of C5H10? Right, from C5H10, we can see that it's got 1 ring in it because it's not, if it had no rings, it would be C5H12, you know, N, 2N plus 2, the number of hydrogens. Okay, so it's got 1 ring in it. It's got to be cyclic. Right, so we can, what can we have there? We can obviously have cyclopentane. And then we could have 4 in a cyclic bit with a methyl group on there. That's 2. Then we could have 3, okay, and we could have a methyl group there and a methyl group there. And of course, if I put it there, it'd be exactly the same. So that's just 1. Then we could have both methyl groups coming off the same carbon, like that. And finally, we could have, instead of 2 methyls, we could have an ethyl. Okay, so that gives us 5 altogether. So the answer is C. Okay. Combustion of 1 gram of hydrocarbon gives 3.38 grams of carbon dioxide. So how are we going to go about that? Right, so I'm going to see mole CO2 made when you burn it, 3.38 over the MR of carbon dioxide, which is 44, mass over MR. That is going to give us 0.07681 moles. Okay, so what mass of carbon is that going to give us? Mass of carbon in 1 gram. Well, to give us 1 mole of carbon dioxide, you have 1 mole of carbon, so the number of moles of carbon is the same, multiplied by the mass of the AR of carbon, which is 12, of course, and that gives us 0.9218 grams of carbon. Now, the remainder must be hydrogen, so the mass of hydrogen is going to be 1 minus that. We had 1 gram to start off with, and that's equal to 0.0781. So how many moles of hydrogen have we got? Mass over MR, AR, of course, is 1. So 0.0781 over 1, 0.0781. So that's the moles of hydrogen. And here's our moles of carbon. It's more or less a 1-to-1 ratio. So it's got to be that there, CH. That's the empirical, the simplest ratio of the number of moles of carbon and hydrogen in the compound. Okay. Right, now we have got, what is the molecular formula of the steroid molecule below? Right, so just looking at them, we don't have to count the number of carbons because they've all got C18, haven't they? So that's got to be right. Now, if that were completely saturated, we'd have to have CnH2n plus 2. So that would give us 2 times 18 plus 2, that would give us 38 carbons. Okay. Now, every time we have a double bond or a ring, we subtract 2 hydrogens. Okay. Now, how many rings have we got? We've got 1, 2, 3, 4. So we've got 4 rings. How many double bonds have we got? Well, we have got 1, 2, 3 in the benzene ring. So that's a total of 7. We've got to subtract 2 times 7. So take away 14 hydrogens. 14 from 38 gives us 24. And that, not forget, we've got the 2 oxygens in that molecule. So the answer is A. Okay, that's a bit of a quicker way of doing it rather than counting all of the hydrogens up. It's very easy to make a mistake doing that, of course. Yeah. Okay. By the way, this CnH2n plus 2 and subtracting 2 hydrogens for a double bond in a ring only works if there's carbon, hydrogen, and oxygen in the molecule. If you've got any nitrogen in there, it doesn't work. So be careful of that. Okay. Okay, gas chromatography, which is correct for gas. The components can be identified by the retention time. Yeah, they can be if you compare them against the standard. The relative peak areas give the proportions. That's true. The area under the peak is proportional to the amount of stuff you've got. And the calibration curve is used to confirm the concentrations. You need to calibrate it to relate the area under the peak to a particular concentration. So 1, 2, and 3, A is the answer there. Okay, number 14. Okay, which of the following reactions produces propan-1-ol? Hydrolysis of alkaline hydrolysis, 1-chloropropane. Yeah, that would do it, wouldn't it? You're going to swap that chlorine for an OH. The acid hydrolysis of propyl methanoate. Yeah, so methanoic acid and the alcohol in that ester is propan-1-ol. So that would work if you hydrolyzed it. And the acid hydrolysis of propane nitrile. Okay, that wouldn't work because the acid hydrolysis of that doesn't give you an alcohol. It gives you a carboxylic acid. So you get propanoic acid. So that one wouldn't work. So it's 1 and 2. Which of the compounds could be prepared by reacting benzene with an acyl chloride in the presence of a halogen carrier? Okay, so what happens in this? You have an acyl chloride. And the halogen carrier will turn that into a into the electrophile. And that's then going to stick onto the benzene ring. Okay, so you can see here that this one you couldn't do that because it's not the carbon-al-carbon that's joining onto the benzene. Here, this would work because it's the carbon-al-carbon that is joining onto the benzene. So you can see you're sticking on that. So you'd use methanoyl chloride for that. And this one here, it's the carbon-al-carbon which is sticking onto the benzene. So you'd use ethanoyl chloride for that one. Okay, so 2 and 3 are the answers. So C it is. Okay, finish the multiple choice now. Okay. Right. Okay, so we have got the hydrocarbon below. Hydrocarbon can be reacted with bromine in the presence of ultraviolet light to prepare this compound, which I've drawn this. So drawn the skeletal formula of it below. Now, what's the name of that compound? Okay, so we number it from this one, 1, 2, 3, 4. So it's 2 bromo. It's 2 bromo. Butane. There's 4 carbons, but we've also got these 2 methyl groups in here. So it's 2 bromo, 3 dimethyl. Two bromo, 3,3-dimethyl butane. Okay, so this compound has stereoisomers. Okay, what kind of stereoisomerism have we got here? Well, you can see, right, it's going to be optical isomerism. There's no stereoisomerism, it's either going to be EZ, in which case you need a double bond, and we haven't got one, or optical isomerism. And that carbon there, number 2, would be asymmetric, so you can have optical isomers because it's got 4 different groups attached. It's got bromine, it's got a methyl group, it's got a hydrogen, which of course we haven't drawn on it, and then it's got this this big group here. Okay, so it's optical is the answer for that bit there. And definition of stereoisomers, I think you learn your definition of stereoisomers. It is same molecular and structural formula, but different arrangement of atoms or groups in space. Okay, right, so we've now got to let's copy that for a minute. What we're going to do now is we've got to draw 3D diagrams to show the stereoisomerism of that compound. So I'll just paste that in there. Right. Right, looking at carbon number 2, we're going to go around that one. So I'm going to draw this carbon number 2. Right, you're going to have a bromine sticking out 3D. We're going to have a methyl. Let's have that one going back into the plane of the paper. So that's methyl. And we've got a hydrogen in the same plane as the paper. And then sticking up in the same plane, we're going to have this thing with 3 methyls. Okay, so that's one stereoisomer, and we've got to draw the other one, which is going to be a mirror image of that. So I'm going to draw an imaginary mirror there, and I've just got to draw the exact mirror image of that. So we've got a methyl group going into the plane there, got bromine sticking out, hydrogen in the plane of the paper, and then sticking up in the plane of the paper, we have the trimethyl group. Okay, so that is our 3D diagrams. That is the way to do them, always. They ask you to draw optical isomers. Okay, now complete the table to show the mechanism for the reaction of bromine to form the compound, right? So it's a free radical substitution reaction. And so you've got to use dots to show the position of the unpaired electron. Now, if you look, paste that in again. So yeah, the bromine has got to go in at carbon number 2. Okay, so right, the initiation step, of course, is always Br2, and with UV light, you're going to get 2 bromine free radicals. Okay, and then in the first propagation step, a bromine free radical is going to react with that. It's going to pull a hydrogen off that carbon there to make a free radical. Okay, so we need to draw our dot on that carbon, and the hydrogen joins up with the bromine to form HBr. Okay, in the next step, now propagation 2, we want this free radical to react with another bromine molecule. So we've got a dot on it there, got Br2, and we're going to form the product. Got our bromine on there, and of course we generate another bromine free radical in doing that. That is the mechanism there. Are they not showing the termination step there? Okay, no. Right, state 2 limitations of using radical substitutions in organic synthesis. Well, first of all, I thought, well, the problem is you get a whole mixture of products. And I was thinking, well, what's the second reason for that? I was thinking maybe it's a violent reaction. So I looked in the mark scheme because I wasn't entirely sure. Well, they actually break this reason down into 2 if you look at the mark scheme. So what they said was, first thing they said, you can get multiple substitutions. So you substitute more than one hydrogen. And then the second thing they said was you get the termination step can lead to a variety of products. Because of course you can, that's what it said in the mark scheme, because the simplest case, you can get these free radicals, they can terminate with each other to form new carbon-carbon bonds. So that ends up, that would make ethene in that case I've drawn there. So you get a whole mixture of things. Again, I wouldn't have necessarily said that until I looked at the mark scheme. I would have put that down as one reason, not 2. Okay. Right. 17, okay, compounds B and C are shown below. They're unsaturated hydrocarbons, okay. B reacts with chlorine at room temperature because it's an alkene, sorry, so you just get electrophilic addition, yeah. Compound C, right, that won't react. There's not an alkene. You'll get, so this one is going to be addition, isn't it? Electrophilic addition, because that's got a benzene ring in it, you're going to get electrophilic substitution. Right, draw the organic structures of the organic product of each reactant action. Right, B is going to give you, right, you're going to, for B, you are just going to get a chlorine on that carbon, you lose the double bond, and a chlorine on that carbon, addition there, just finish it off. Right, for C, you're going to get, right, they react in a 1-to-1 ratio, yeah, so that's 1 mole of chlorine reacting with 1 mole of B. And with C, well, you're going to get 1 mole of chlorine reacting with that, and you're going to get the chlorinated product, and you're going to get HCl. So that's where the other chlorine go. You only stick 1 chlorine on that. So here's the product with C. And it doesn't matter which of those carbons you stick it on because they're all the same, aren't they? They're all equivalent. So I put the chlorine on there. And they're saying the other chlorine from the Cl2 molecule gives you HCl. Okay. Right. 3, explain the relative resistance to chlorination of compound C compared to B. Right. So first of all, we're going to say there's 3 marks here. So I think I'm going to say B is more reactive because it's got a higher electron density. On the pi bond. Okay. Right. It's got a high electron density in B because, you know, between those 2 carbons, you've got 2 pi electrons between those 2 carbons. Whereas if you because this is delocalized, you've only got like 1.5 pi electrons between each of those carbons, because it's spread out. The double bond is spread out over like between 6 carbons there. Okay, yeah, it's delocalized system, so that would make it more reactive. And I think the second thing I would say, obviously, is I think you need to say delocalized electrons in C, and if you chlorinate C, you're going to disrupt the delocalized system, and of course that is going to be energetically unfavorable. Okay, right, outline the mechanism for the reaction of compound C with chlorine and show the role of the halogen carrier. Okay, right, so the first step, we're going to have the reaction of the halogen carrier, aluminium chloride plus Cl2. You're going to make AlCl4 minus, and the electrophile, which is chlorine with a plus on it. Okay, now the next, let's draw the mechanism here then. So we've got Cl plus. Now draw the electrons are going to come from the delocalizer, from that ring onto the electrophile. I'll draw this bigger. Right, so you've got that there. Let's say we've got the chlorine and is now stuck onto that carbon. So we've partially disrupted the delocalized system. So we draw the ring like that, incomplete, and there's a positive charge being shared on that ring. And we draw the hydrogen. We actually draw that hydrogen in because we've got to show. So the next step, the final step, is that pair of electrons goes back into the ring, and so we're going to form there the product. Delocalized, it reforms. You've got a chlorine on there, and you've got the methyl groups there, and we're going to have H plus. Now finally we need to show the regeneration of the catalyst, because the catalyst is turned into that. So the catalyst is regenerated, AlCl4 minus. It's 5 marks going for this, so it's obviously going to have to not just show the curly arrow mechanism, but you're going to have to show the other bits to get the marks. There's a lot of marks going for that. Plus H plus, and that's going to give you AlCl3, regenerated the catalyst, and you will get H, hydrogen chloride gas. Okay, so compound C can be prepared by the trimerization, that's getting 3 identical things together, of propanone using concentrated sulfuric acid catalyst. Suggest an equation for this reaction using molecular formulae. Right, so the molecular formula of this thing here, of our that's going to be, well, 6 carbons in the benzene ring plus 3 others. That's going to be C9. How many hydrogens? We've got 1 there, 2, 3. We've got 3, and we've got 3 there, 6, 3 there, 9, 3 there, 12. H12. Okay, that is the compound. Right, and propanone, well, that is what's the molecular form of propanone. So it's CH3C. So that's C3H6O. And we're going to have 3 of those. So 3 C3H6Os. And that's going to turn into C9H12. Right, we've obviously got 3 oxygens there, and if in doubt, we were wondering where your oxygens go. They usually end up being water. So let's make 3 waters there. I think you'll find you've got the right number of hydrogens there, because let's see, we've got 12 hydrogens there, plus 3 lots of 2, 6. That's 18 hydrogens on this side of the equation. And we've got 3 times 6 there. That's 18 hydrogens on that side. So that equation is balanced. Okay, so this compound D, chemist proposes a synthesis of D from C. Predict the number of 13C peaks in the 13C NMR spectral peaks in compounds C and D. Right, let's do C first of all. We've got quite a lot of symmetry going on there. So you can see that one, and that carbon, they're all the same. So that's 1 peak. These carbons are all the same. That's 2 peaks. And these methyls, these are all the same as well. So that's just going to be 3 peaks in that one. Now all that symmetry's largely disappeared here. So there's going to be a lot more peaks in this compound D. So let's do that. So we're going to have these 2 the same. Call that 1 and 1. These 2 are the same, 2. That one is unique, 3. These are the same, number 4, 4. That's 5, that's unique, and 6 is unique, 6. And then we've got 7 there and 8 there. So that is going to be 8 peaks in compound D. Okay, so now develops a 3-stage synthesis of D to C, complete the flow chart. Okay, right, now how are we going to, what we can see here, right, so we've got 3 steps, but for this step, we're using tin and hydrochloric acid. Now, tin and hydrochloric acid, the only thing they ever reacts with, that will reduce a nitro group on a benzene ring to an amine group. So that's what's happening there. So now, if we look here, look, we've stuck one. That originally was an NH2 group, okay? And so we're going to stick a nitro group on there. Okay, that's what we're going to do. And then we're going to reduce it. So I'm going to do that there. So that's what that tin and hydrochloric acid was a bit of a clue, really, what was going on. So we've got our NO2 on there. Then I'm going to reduce the NO2 to the amine. Okay, and then you can see what they've done there is they've acylated the amine. They've stuck that group on to this NH2 here. Okay, so let's think about the reagents for all of that then. Well, sticking a nitro group onto a benzene ring, you want conc nitric acid, and you'll need a conc sulfuric acid as a catalyst. The reagents and conditions are done for us in this second step. Let's think about the reagents there. What we're doing, we're sticking an acyl group on there. So we want to stick, let's just draw out that. A carboxylic acid won't react with an amine. It's not reactive. It's got to be an acyl chloride, isn't it? So that's what we want. We want ethanoyl chloride. To do that. Right, that is halfway. So I'm going to leave that there and do the next half in the next video.